In this video, we will consider how to apply Newton's second law to the case of systems where the mass of the system changes. In such cases, F equals ma is no longer valid, and we will instead go to the original form of F is equal to the rate of change of momentum, p. For our first case, we will consider the classic scenario of a rocket. At time t1, the rocket has a mass m1 and a velocity v1, as seen by an inertial observer O. At time t2, the mass of the rocket is now m2 and its velocity is v2, and it has expelled some gas, which could be heading either backward or forward, but we will say that it has a velocity v gas as seen by the observer O. Now, our system here actually doesn't change its mass because we will include both the rocket as well as the gas. So at least in this time interval from T1 to T2, the mass of the system hasn't changed. The momentum of the system at time T1 was P1 equal to M1 times V1. And at T2, we have the momentum of the rocket plus the momentum of the gas. Since the mass of the rocket is now M2, we expect that the mass of the gas will be m1 minus m2. The notation that we're using for the velocities is v a slash b is velocity of a with respect to b. Using the relation between various relative velocities, we can rewrite velocity of the gas with respect to observer O as velocity of the gas with respect to the rocket plus velocity of the rocket with respect to the observer. But the velocity of the rocket with respect to the observer is now just v2 slash O. We now make a notational change. Instead of T1, we write T. Instead of M1, we write M. V1 is V and P1 is P. And now we say T2 is T plus dt. M2 is M plus dm. V2 is V plus dv. And P2 is P plus dp. So notice that all these terms have had a change, an infinitesimal change. And so now our time difference is just an infinitesimal time difference. And this will allow us to set up a differential relationship between various quantities. In particular, note that even though M2 is less than M1, we are writing it as M plus dm. Again, let me reiterate that in order to get the right signs at the end, all these quantities that happen at the later time are written as T plus an infinitesimal change dt, M plus an infinitesimal change dm, V plus dv, P plus dp. Thus, in our new notation, we have at time t, we have P equals mv, and at time t plus dt, we have P plus dp equals the following quantities. We will now simplify these expressions using the rule that the product of any two infinitesimal quantities will be ignored. Thus, when we expand this product, the term dm times dv will be ignored, and similarly over here. With this in mind, at t plus dt, we can expand out the various products, and we get it down to this, and we see further that this term will cancel with this one. So we have this for our momentum at t plus dt. Therefore, looking at the change in momentum of the system, that is p plus dp minus p, we have the following, and we have one more cancellation that takes place, leaving us with dp equals mdv minus dm times the velocity of the gas with respect to the rocket. If there is an external force, then dp is just F external times dt. And so we have F external times dt equals dp equals this quantity. In this example, we will consider the case of a rocket in space with no external forces. So F external is 0, and we get the following equality. To make life a little simpler, we will rewrite dv as the scalar quantity dv times x hat. And again, this vector v gas with respect to the rocket as the scalar quantity. And you can see that we've introduced a minus sign because with respect to the rocket, the gas is headed in the negative x hat direction. So we have the magnitude v gas with respect to the rocket and then times minus x hat. Rearranging, we have minus dm over m is equal to dv over v gas with respect to the rocket. Remember here that v is the velocity of the rocket itself with respect to the inertial observer. Integrating, since v is the velocity of the rocket with respect to the observer, it is a different variable compared to the velocity of the gas with respect to the rocket. In fact, this quantity is the velocity of the exhaust with respect to the rocket and is often fairly constant. So it can be pulled out. And we have integral from 0 to v dv. And this integral on the other side where the mass is changing from an initial mass to a final mass. This is a simple enough integral. And so we get the following final relationship, where we've absorbed the minus sign to flip the log. And since m initial is greater than m final, this will give us a positive value here for this natural log. And this exhaust speed out here is a positive number. And so we get a positive final velocity for the rocket. Let us look at another example. In this example, we have a freight car of mass m containing a quantity of sand of mass little m. At t equals 0, a constant horizontal force of magnitude F is applied in the direction of rolling. And at the same time, a port in the bottom is opened to let the sand flow out at a constant rate, dm over dt equals b, where b is a positive constant. Assume the freight car is at rest at t equals 0, ignore friction, and find the speed of the freight car when all the sand is gone. In the problem statement, we use capital M for the mass of the freight car and little m for the initial mass of the sand in the freight car. So to avoid confusion, we will use mu of t as our symbol for the time-varying mass of the freight car plus sand in it system. We start with two generic times t1 and t2. This is important. These are generic times. They are not at the actual start of the process. They are not at the actual finish of the process. These are just two times t1 and t2 in the middle of the process we are examining. At time t1, the momentum of the system is mu1 times v1. Mu1 here, remember, is the mass of the freight car plus whatever sand is in it at this moment t1. And all of it is moving at a speed of v1. A short time later, at time t2, the freight car has mass mu2 and velocity v2, and it has released some sand through the port. This sand, however, of course, is still moving. Now, is it moving with velocity v1 or velocity v2 or something in between? Well, probably something in between, but we will take it as v1, and we will see later on that, in fact, whether we assume this to be v1 or v2 doesn't actually affect our calculation. So we have started with a particular system at time t1, and we're keeping track of everything that was in that system. And the momentum now is mu2 times v2. This is the contribution from the freight car. And mu1 minus mu2 times v1 for the contribution of the sand. Eventually, of course, the sand will hit the ground and come to a stop, but that is outside our purview because that's further external forces on the sand, and we really are just concerned with the freight car in the end. Now, changing to our notation of t and t plus dt and so on, we have the initial momentum is mu v, and this is our final momentum. Looking at the change in momentum, we get the following expression for dp, and we simplify it while keeping in mind that doubly infinitesimal terms can be ignored. This time there is an external force, so we can equate dp to f times dt. Since all this is taking place in one dimension, we remove the vector symbols and just go to components. We have fx dt equals mu times ddx. And we can rearrange that. Remember here that mu is the time-varying mass of the freight car plus whatever sand is in it at that time. So it is a function of time. So it has to be on the same side as dt. F, however, is a constant. We could put it on either side. We'll move it to the side with the velocity. What do we know about mu? We know that mu is equal to capital M plus little m at t equals 0, and that it is changing at a constant rate b. And so we have that mu of t is the quantity m plus m minus bt. Plugging that in, we have this expression, this differential relation, and we can integrate both sides. On the right-hand side, we're going from 0 velocity when the freight car is at rest to whatever its final velocity is when all the sand is gone. And on the left-hand side, we're going from time t equals 0 to the time little m over b, because that is how long it would take for all the sand to come out. Integrating, we get the following relation.
And we can rearrange to this expression, where we note that f and b are both positive constants, and big M plus little m over big M is a number greater than 1, and so the natural logarithm will be a positive value, again giving us a positive final velocity.